Good morning, everyone. I'm João, and my work is multidisciplinary design and optimization of hybrid electric ultrasilent high aspect ratio wings, and is being performed in collaboration with Dr. Andrea Cini and Rano Cavallaro, and it is deeply connected to the Indigo project. Okay. So basically, my work will be centered around straight-braced aircraft wings, being one of the driving factors for this configuration. The more stricter regulations regarding environmental rules in the future and standard noises, but it is also a configuration that has a strut, which has the possibility of improving the overall aircraft performance by allowing wings with higher aspect ratios and therefore lower induced drags and thereby increasing the lift to drag ratio. That support also has the possibility of decreasing the wing weight and therefore minimize the overall aircraft weight. So basically, this is the problem that we intend to solve, where we have this wing shape planform with a leading edge with a sweep angle equal to 0, and then we basically have a tapering after half midspan. And we intend to vary these input parameters to minimize the mass, being 5 of them relative to the wing. The aspect ratio, taper ratio, projected area, and thickness to chord ratio on both tip and root. And for the strut, we basically want to vary the chord for now, maintaining the attachment at half of the midspan. So this is the work that we have performed so far. Basically, our strategy was to develop a parametric global finite element model, where basically only the wing box of the lifting structures is defined. We wanted to go a bit further regarding the state of the art, and therefore we also modeled the section of the fuselage, which is in contact with both the wing and the strut. Regarding the connection between the wing and the fuselage, we use the ATR-42 as an inspiration, so the connection is a high wing, and the connection is inspired on that aircraft. And then regarding the connection between the strut and the fuselage, we did a couple of experiments, and then we ended up with this solution, where basically we are taking advantage of the space below the cargo floor to maintain the airplane capacity, while having a wing box to minimize the mass and to distribute the loads to the frames of the aircraft. So most of the GFM is modeled using shell elements, also the stringers, because we wanted also to consider composites on the stringers. And regarding the redistribution, we followed the A320 redistribution because it's our reference aircraft. Nevertheless, we did some adaptations to that in order to have a rib in each spanwise position connected to an engine, being the engines and motors modeled as concentrated masses, which are connected to the wing ribs using RBE elements. This is also one of the works that we performed. So we considered strut-braced wings, but we also wanted to see the effects of considering hinges in 3 different positions. So being the first one between the wing and the connection between the wing and the strut, the second one between the connector and the strut, and the third one between the strut and the fuselage. To save computational time, we basically simplified the GFM into a beam model with a cross-section of a wing box, and we did a weight minimization. and we reached the conclusion that it was more advantageous to minimize the mass, having only an inch in the position tree, so between the strut and the fuselage. These are the load cases that we are considering now. So being the first one, the most exigent in terms of load factor, 2.5 Gs. And we are also considering these design constraints, being the strength, buckling, and tip displacement, the constraints which are basically sizing our model at the moment. We also intend to maybe consider fatigue and air elastic constraints, but that is something that we may add when in the next steps of this work and thesis, which also intends to increase the fidelity of our model. To finalize this presentation, this is also one of the things that we intend to do and which we will be doing in the next 2 weeks. So basically, we are using weight estimation formulas from traditional aircraft design books, which most of them are not adapted to this type of configuration, and therefore we found this flight optimization system weight estimation method, which is more adapted to distributed propulsion, and that has terms within which consider strut braced wings and factors that depend on the composite utilization. And so the idea will be to basically use our GFM to calibrate these factors and reach to formula that allow us to have a low fidelity weight estimation with a bit of more, with a less error per se. Okay, so regarding the future work, after we finish this work, we intend to prepare a conference paper and a journal paper. As I mentioned, we also plan to increase the fidelity of GFM, for instance, by modeling the nacelles, positioning the landing gear, and doing detail design. And we will also explore alternative machine learning methods to minimize the computational costs during the optimization process. So thank you very much. I'll be happy to answer your questions.